everybody. I'm going to talk to you about section 13.1 right now. You'll be reading this for Monday, but I'm going to talk you through some of it so you can work on the worksheet after this and feel pretty good about Monday when we do a lab that applies a lot of this information. So 13.1 is compounds and aqueous solutions. We've talked about some of this stuff already. It's just kind of putting in a little bit different words, a little bit different types of things we're doing here. So here we go. First of all, in 13.1, you'll see that there's dissociation equations. So you have this on your sheet that has been given to you. And there's a couple different examples that you have there. And this is just an equation showing what happens when a solid, in this case NaCl, breaks apart with water being there. If NaCl, when it breaks apart, it breaks into two separate ions. So NaCl is a solid, so that's why it has an S here. And then when it's become its ions, those ions are considered aqueous. So that is one example of a dissociation equation. You also have another example of a dissociation equation, and that would be for aluminum chloride. Aluminum chloride also dissolves in water. Not all ionic compounds dissolve in water easily, but aluminum chloride does. And so if it's a solid, and it also, with water, will form aluminum, which is a 3+ ion, which is aqueous, plus 3 chlorides for every 1 aluminum. So we are separating our ions by how many there are. So don't get caught up doing this, that there's a Cl3. There's actually 3 chlorides for every 1 aluminum. So that's why it's written that way. So that's called a dissociation equation. And that just helps us understand, okay, how does an ionic compound break apart? If it's a molecule, it would just break into its molecules. But if it's an ionic compound, it's going to break into its individual ions. So this is called a dissociation equation. Next type of equation is going back to chapter 8 and just talking about double displacement. And you also have this on your sheet. It's already given to you. Lead 2 nitrate plus potassium iodide. This is actually an example that we did back in chapter 8 in our notes. Lead 2 nitrate plus potassium iodide, and then no products that are made. So it does make a precipitate, and I know that just from because I've shown this demo before. But also, one of these two products is not soluble in water. In the past, we used page 437 to look that up, and you'll need to do that again when we're doing 13.1. So 437 is the page to have open. So I'll let you get that open right now, if you didn't already have it there. Alright, so we're just going to go ahead and write this out and put our formulas here. Lead 2 nitrate, lead is a +2, nitrate is a -1, so it's going to be PbNO3 with the 2 behind it, and that is aqueous. Remember, with a double displacement reaction, we have 2 aqueous solutions combining. Potassium is a +1, iodide is a -1, so it's going to be just Ki. And it's going to form lead 2 iodide. Again, lead's a +2, iodine's a -1, so it's PbI2 plus potassium nitrate. Potassium's a +1, nitrate's a -1. Alright, if you look at page 437, there's a couple rules that apply to potassium nitrate. Potassium compounds are always soluble. Rule number 1, or guideline number 1. And also guideline number 2, nitrates are always also soluble. So this is definitely a soluble solution, or aqueous. But the iodide is not even shown on page 437, just because I told you a precipitate is formed in this reaction. This, by default has to be the precipitate. Any examples I give you, you'll definitely be able to tell from page 437. But in this case, this lead iodide is not soluble, so that makes it the precipitate, which makes it a solid. Page 437 is some guidelines, but it's not all of the solubility rules. There is other rules that can be applied. If you take AP Chemistry, you'll get to know those pretty well. All right, so that is a formula equation that we did back in Chapter 8. Now let's move on and balance that. If you look at the back of your sheet, you already have that balanced. All right. Now, something that we have not done yet, but you'll also see in section 13.1, is called an overall ionic equation. We've alluded to this a little bit. We've discussed it a little bit. But the overall ionic equation is taking those compounds and breaking them apart into their individual ions, kind of like what we did with the dissociation equation right at the beginning here. So we're taking lead. We have two lead ions, but they're a +2 charge. We have two nitrate ions, so that's why we show that there with the charge and with the aqueous sign. We have two potassium ions and two iodide ions. Because they're soluble, they will form those ions. And in reality, they're not together as potassium iodide or together as lead 2 nitrate. In reality, in the solution, those ions are free. They are not connected. So an overall ionic equation shows that. And then on the right side of the equation, we have the two potassiums from here, the two nitrates from the potassium nitrate, but lead 2 iodide is not aqueous, so it is not broken apart. It is together. Those two ions are together as a solid, as a compound sitting at the bottom of the test tube. So that's why that stays together as a solid. Now, that's the overall ionic equation. All the ions that are involved and that are existing and that you could see if you had that ultimate superpower, being able to see ions and compounds and everything else. But what's next is called the net ionic equation. And the net ionic equation comes from getting rid of what's called the spectator ions. So our spectator ions are ions that are on both sides of the arrow. They're in the reactants, and they're on the product side. And they don't really do anything. They're not making a solid. They're just spectators. They're not players in the game. They're spectators. So if we look at this, these nitrates are on the left, and then they're on the right. Those are spectators. The potassiums are on the left, and they're on the right. They're called spectator ions. Spectator ions. That's what those guys are. So if we eliminate those, so the overall ionic equation contains them, but if we eliminate those, what we have left is called the net ionic equation. What actually occurs in the end, and what chemical reaction really happened, is called the net ionic equation. So we'll get to that here. That is what is left, is Pb ions, lead ions, forming with iodide ions to make lead 2 iodide. That's what really occurred here, because those other ions didn't do anything. They were just there in the beginning and the end. So that's why they're considered spectator ions. So in review, we're doing a balanced chemical equation like we did in Chapter 8. We then just break up if you have a precipitation reaction. So you form a solid, one of them from page 437. We're breaking up anything that's aqueous into its individual ions. Notice that it needs to be a balanced equation so those individual ions can cancel out in the end. We have spectator ions that then will get eliminated or removed in the overall, or in the net, for the net ionic equation. And what's left are the ions that are actually forming together to make that precipitate. You are now going to try the last, or the next thing, and I would like you to try this yourself, and then I will go over that in a little bit, how you can get those answers. So silver nitrate plus sodium chloride. Go ahead and try to predict the products, write out the balanced chemical equation, write out the overall ionic equation, write out the net ionic equation for silver nitrate plus sodium chloride.